Okay guys, here goes my third attempt at trying to make this video. I tried sitting outside, it was nice, it was sunny, birds, and the neighbor kids are so loud that I couldn't concentrate on what I was doing. And I thought it would drive you nuts too if you were trying to listen to this video. So it's a little bit darker down here. I thought I had brighter lights, but I guess not. Oh well, hopefully you can see the page perfectly fine, and hopefully you did this question before pressing play on this video because I wanted you to get an answer. You knew how to do this in grade 11, it's no problem. Okay, so to start off, we are calculating the speed of an object after it drops and falls from the top of the Skyline Tower, and luckily you have my awesome graphic here to guide you along the way. Look at that. Now that is a university professor drawing, if I do say so myself. Okay, so you would have done this in grade 11 and you would have used conservation of energy, no problem. You would have said that the total energy in the beginning is equal to the total energy in the end. And you probably stopped writing that formula over and over in grade 11 because you just thought it was kind of obvious. But I'd still like you to continue writing that formula. It's going to get more and more important now, actually. So if you started off at the top of the Skyline Tower, the total energy in the beginning would be all gravitational because it would be all height energy. There would be no speed in the beginning. And when you drop the object and it falls all the way down to the ground, just before it hits the ground, it would be traveling very, very fast. So it's got kinetic energy and no more height left because it's fallen as far as it possibly can. So that would be your expression. And then you flip to your formula sheet in grade 11. mgh for gravitational energy, 1/2 mv squared for kinetic energy. You always canceled the mass, left side, right side, or most of the time you canceled the mass. And that was it. You rearranged for whatever you were solving for, in this case, v. Might be a little bit easier to write v squared. I'm just going to move the 1/2 over. gh divided by 1/2. Should be the answer to this question. And then make your substitutions. G is 9.8 meters per second squared. The height of the Skylon is 160 to the observation deck. Divide by 1/2. And don't forget to square root the answer in the end. I kind of ran out of space here, so I'm going to go up here. Okay, so 9.8 multiplied by 160 divided by 1/2, and don't forget to take the root of it. You get 56 meters a second, no decimals. Okay, and this question asks express the answer in kilometers an hour, so do a quick conversion on that and you'll get the final answer, 201.6 kilometers per hour. And that would have been the true and final answer in grade 11, but come on. You go up the Skyline Tower and drop a penny. It's not going to hit the ground at 202 kilometers an hour. That would kill somebody. Well, maybe not kill them, but it would certainly hurt. It would maybe crack their skull a little bit. This is the old adage about if you drop a penny off the Skyline Tower, will it kill somebody? Or could you dent a car when the penny gets to the bottom because it's traveling so fast? Yeah, that probably would. But that's not what actually happens. Because one thing we didn't do in grade 11 is we didn't consider wind resistance. Everything was as if it was happening in outer space. I mean, I never really said that, but all the calculations were completely devoid of any kind of wind resistance whatsoever. And we really should have put that in. It's a very simple modification. So let's do this question again. But let's do it a more proper grade 12 way with one little detail in here. And yeah, it's a very specific number because I'm looking for a specific final answer here just for this example. What if there's a constant force of wind resistance of 0.019552? A very, 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 very small force, but a force that can't be avoided. Well, whenever you had a force of friction, you could calculate energy. We did do that in grade 11. We called it work. Work equals force of friction times distance. And you did this multiple times in grade 11. Well, work is energy. So this is another form of energy. It's just called work. But don't make that mistake in thinking that work isn't energy. It is energy. It's just a totally different kind of energy. It's energy due to things rubbing together or dragging across the surface. In this case, the penny falls and it drags through the wind. So let's do this question again, but let's add in this detail. Here's how the question should be done. Total energy in the beginning equals total energy in the end. And remember what total means. Total means add them up. Conservation of energy formulas always have plus signs. Plus, 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 plus. Everything's plus. You add everything together. In the beginning, you have nothing but gravitational energy. In the end, as the penny falls, the energy splits into two different forms. Some of it will, of course, be kinetic energy as it builds up speed. But some of the energy is going to be work. Some of the energy is going to be converted into heat because of the penny rubbing its way through the air. And that heat is going to dissipate into the environment. If you caught the penny at the bottom of the tower, I don't think the penny would feel hot. It generates heat, and it's losing that heat into the environment. But even though it's losing it, see, losing sounds like you're subtracting it off. No, it's all plus signs, because you say to yourself, maybe if I go to this diagram here, as it falls, some of the energy is dissipated into the environment due to work. Some of the energy arrives at the ground as kinetic. There are two forms of energy, and if you added them together, you would get what you had in the beginning, the gravitational energy. So even though heat is being lost, don't think of the word lost as a negative sign. Or you could think of it like this. You're solving for kinetic energy. So when you bring W to the other side, yes, then there's a negative sign. So there's where the loss starts coming in. You're subtracting off the work energy from the original gravitational to get the kinetic energy in the end. Let's break down our variables here. Actually, I want to show you something. No, I'll do it after. Okay, so gravitational energy is mgh. Work is, I'll put it in brackets just so we don't get a bed mass error here, force of friction times distance. And kinetic energy is 1/2 mv squared. Well, here's one of the other reasons we didn't do it in grade 11, because I didn't want to confuse you with the masses. You need a mass in every term if you're going to cancel it out. And there isn't a mass in every one of these energy terms. The work formula just has force of friction times distance. I suppose if you broke down force of friction into subvariables, you might be able to get another mass out of it and cancel it. But this question gives you the force of friction as a magnitude. So you don't know the values that multiply together to give force of friction, and you can't cancel mass. So the penny's mass is going to matter in this question. Okay, we're solving for v squared, so I need to keep isolating here because this isn't fully isolated. Let me write that again. mgh minus force of friction times distance divided by 1/2 m equals v squared, and you can't cancel the mass, so the substitution is going to be longer, but that's the only difference. Like, really, nothing's changed here except adding in that other energy. So what do we got? The mass of the penny is 2 grams, which is 0.002 kilograms. Gravity is 9.8. The initial height was 160. The force of friction, a very specific value in this question, 0.019552 newtons. And that happens over a distance of 160 meters. And then we divide by 1/2 m. M is still the penny, 0.002 kilograms. Okay, so work all that out and you'll get the answer. But actually, and I don't usually do this, but I'm going to write another line below this one just to show you the two energies on top as numerical values. So let me calculate the first energy, the gravitational energy. That comes out to 3.136 joules. So that's how much energy there was in the beginning at the top of the tower. The friction coming off of this is going to cause heat energy. And the value is 3.1283 joules. So you can see most of the energy that was there in the beginning is actually going to get burned off as heat on the way down. And there's not going to be very much energy left to be converted into kinetic energy at the bottom. Okay, let me put the other values on the bottom of that calculation. Okay, so now you get a more appropriate answer. So let me calculate this. 3.136 minus 3.1283 divided by half and divided by 0.002 is, whoops, I think I screwed that up. Sorry, I got to do that again. I did mess it up. 3.1283 divided by half divided by 0.002 gives a final answer of 7.7 meters per second. That's more appropriate. If you convert that into kilometers an hour, you are looking at 28 kilometers an hour. Sorry, I can't fit that in there at the bottom of the page. That's a more appropriate value. You get bonked off the head with a penny traveling 28 kilometers an hour. You'll feel it, but I mean that's extremely slow. So this is what we're doing: is we're gonna repeat some questions that are objects moving in the up and down direction, but we're going to try and include work in there as a loss due to friction. I've got 3 practice questions for you here. The first one is a girl going down a slide. And see, like in grade 11, we might have done that question, but the girl's butt is in contact with the slide. Like as she's sliding down the slide, you can't possibly take all your gravitational energy at the top of a slide and convert it into kinetic energy at the bottom of the slide, because your body is in contact with the metal or the plastic of the slide as you go down. So she starts off at the top of a oh, there's a value missing here. Shoot, you know what? I wrote this question and I deleted a value by accident. You need to fix this question. Okay, I'm going to put the proper question. There's no height. It says that the slide is 10 meters long, but it doesn't give you the height of the slide, and you need height, of course. So let me add that in, and please fix that question. I'm going to put it in the description of today's lecture, and do that question. She arrives at the bottom of the slide with a speed of 2.5 meters a second, which is not fast enough for if this was a grade 11 question, because she's going to lose heat energy as she slides down the slide. So try the question out and see if you can get that as an answer. Question 2, you're dropping an anchor through some water, so it's very much like the question that we just did in this example. As the anchor doesn't free fall. As the anchor drops through the water, it encounters a buoyancy force, which is just like wind resistance in the example. There's a force of 489.7 newtons on the anchor as it descends. Then try question 3. Now question 3 is truly and honestly a grade 12 question. It's not a freely falling object. It's just like question 1. It's an object on a ramp. The object is sliding down the ramp, but let's go back a couple of steps. This question gives you a coefficient of friction. It's so the force of friction isn't necessarily just given as a force. You need to work it out, etc. There's a lot of things going on in question 3, and there's various different ways to do it. So we're going to take up these questions to end off the week tomorrow, and we're going to focus on number 3. We're actually going to take up number 3 2 different ways. We're going to do it the way that you could have done it earlier in this course when we were looking at objects on ramps, and that'll be great review. And we're also going to do this question again using energy conservation and work it out that way. So, and it's going to be long. The solutions are long both ways, so that's why it's going to take up all tomorrow. But I want you to try it first. So do number 3 however you want to do it. Actually, you know what? Do number 3, but use only energy. Don't do it the old way. I will do it the old way on the video tomorrow, and we'll take it up together. But do it using energy formulas if you can, and see if you can get an answer of 1412. And if you don't, just leave your answer. Leave your wrong answer that isn't 1412, so you can debug tomorrow when we take it up together and try to find out what that mistake was. There's nothing new here. It's kind of just engineering intuition using formulas that you've already learned.